So we want to talk a little bit about conversions. And we're going to start out with the standard system doing our conversions. And we're going to talk about something called dimensional analysis. Now, dimensional analysis, we mentioned it briefly in the last unit when we were talking about fractions. Dimensional analysis actually can help us figure out what to do in a problem. If we look at it as, let's say we're traveling at 35 miles per hour. And I write it like this, it's 35 miles per hour instead of mph. That actually is a relationship or a ratio of 35 miles over 1 hour. It's a rate. If we want to know how long or how far we can travel in 7 hours, by using the units and by setting it up like this, we have two different options here. One, we can use a proportion. So we'd have 35 miles over 1 hour equals, well, the hours have to go with hours, so our 7 hours has to go on bottom. And to find that missing number, which is going to be miles, we can cross multiply and divide. 35 times 7 is 245. Divided by 1 is just 245. And the units do work out. If you look at the units, 35 times 7 is 245. Miles times hours would be a mile times an hour. And then we divide by the 1 hour. When you divide by the 1 hour, the hours divide out and you are left with miles. Well, in a proportion like that, cross-multiplying and dividing, it's a little bit clumsy. So it's easier to use a little more straightforward form of dimensional analysis, which is, I'm going to take my 7 hours and I'm going to convert it into miles. And the way I'm going to do that is I'm going to put 7 hours over 1. And I have this relationship here. 35 miles per hour is the same as saying that 35 miles is equivalent to 1 hour of time. And I use that as a conversion factor. So I come down here, I want to get rid of hours. So I'm going to put hours on bottom here. And I'm converting to miles. So 35 miles to 1 hour. And in my fractions here, you can see the hours cross-cancel out. And now I have 7 times 35 miles is 245 miles. And 1 times 1 is 1. So 245 miles over 1 are just 245 miles. So the units cancel themselves out. We do our conversion by canceling out the units. By doing it this way, we don't have to remember, do we multiply, do we divide, whatever. Right? Sure, if you remember back to doing measurement conversions when you were younger, you know, going from feet to inches, you got to remember, going from inches to feet, we divide, feet to inches, we multiply. Well, by using dimensional analysis, we don't have to remember that because all we have to do is set it up so that it cancels out the units, and then the rest of it takes care of itself. Once it's set up, the operations can only work a certain way. Now, your textbook takes this idea of dimensional analysis way too far. Some useful dimensional analysis in fact, it's one that's going to come up for us quite a bit in our next unit. We might have, flow rate of, let's say it's doing 20 milliliters per minute. We want to know how long it'll take, how long to infuse 100 milliliters. So the dimensional analysis here would tell us we have 100 milliliters. Make it a fraction by putting it over 1. Now we want to get rid of milliliters. So we're going to put milliliters on bottom here. And we want to convert it into time. How long? How many minutes? So we're going to put minutes on top. And again, this 20 milliliters per minute can be thought of as 20 milliliters is equivalent to 1 minute. So what that means is we're going to put 20 milliliters on bottom and 1 minute on top. So even though this is 20 milliliters per minute, we can write it as 1 minute per 20 milliliters. It's the same thing, same relationship. The milliliters cancel out. 100 times 1 minute is 100 minutes. 1 times 20 is 20. And now we just reduce the fraction. Dividing out by 20, that's 5 minutes. That's a useful form of dimensional analysis. In our next unit on dosage calculations, we will use that a lot. You'll note here that we didn't have to know anything about any formulas or any relationship between milliliters and milliliters per minute. We strictly looked at the units, and the units told us what to do with the numbers. We lined up the units so that they canceled out, and then we multiplied across and divided it, reduced down the fraction. Now in the textbook, they'll give you some weird ones like centimeters squared over liters times liters over grams times centimeters, like that. What they're asking you to do here, like a centimeter squared, that's a centimeter times a centimeter, so you can split that up into a centimeter times centimeter. And then you can cross cancel within your fractions. This centimeter cancels out that centimeter. This liter cancels out that liter. What's left on top is just centimeters. What's left on bottom is just grams. So it's centimeters over grams is what you're left with there. Not a horribly useful practice, but it does get you used to canceling out the units for the dimensional analysis. They also tend to do something like this. Give you a centimeter to the -1. In practical application, I don't even know what a centimeter to the -1 would be. You get in physics and in structural engineering, there are some things like elastic modulus and stuff like that that have a meter to the -1 or meter to the -2. That's only defined that way to make the units work out in the rest of your calculation. It really is a meaningless unit itself. Like if I have x to the -1 times x, if I think of this as being x to the 1, when I multiply exponents that have like bases, I keep the base, that's going to stay x. What do I do to the powers when I multiply? I add them. So what is -1 plus 1? It's 0. And what's anything to the power of 0? It's just 1. So if I have centimeters to the -1 times centimeters, that multiplies to make 1. They cancel each other out, basically, is what it's saying. So the textbook, again, keeps going to that extreme, and they'll have something like milligrams squared over liters to the -1, meters to the -1, times liters to the -1 milligrams times meters. So again, just like we did above, milligrams squared is milligrams times milligrams. I'm going to write that out, makes it a little bit easier. So I've got a milligrams here, they'll cross cancel with that milligram. I have this liter -1, which will cross cancel with that liter -1. On top here, all I have is milligrams. On bottom, I have meters to the -1 times meters. Well, that's just a 1. So it's milligrams over 1 or just milligrams. I'm not going to spend any more time doing those examples like that with just the units because, like I said, in practical application, those aren't very practical. What they're there for is to get you used to looking at the units and canceling out the units and working with just the units. So I'm not saying it's a useless exercise. It isn't. But the practicality of it is not there beyond just training you to get used to working with the units. So for our purposes, when we go to convert measurements, if I have 7 pounds and I want to convert it into ounces, I need to find a relationship somewhere between pounds and ounces. And if we look back in our tables we've looked at here, we find we've got the relationship 1 pound equals 16 ounces. So what we do is we set this up, make the 7 pounds into a fraction by making it 7 pounds over 1. Now we have pounds here, so to get rid of pounds, we have to put pounds on bottom. In our relationship, 1 pound is 16 ounces, so this is 1 pound on bottom. On top is going to be 16 ounces. Now before I go any further, I'll make one more side note. If you remember when we were doing fractions, we had 2/3, and we might multiply that by 5 over 5. 2 times 5 is 10. 3 times 5 is 15. And we said 10/15 has exactly the same value as 2/3. Because 5 over 5 is equal to 1. We called that a unity fraction. When you multiply by a unity fraction, or when you multiply by 1, you can change the appearance of a number, but not its value. That's exactly what we're doing down here. This does not necessarily look like a unity fraction, but it is. 16 ounces and 1 pound are the same thing. So it really does have a value of 1. So now the pounds cross-cancel out. I have 7 times 16, which is 112. Now it's ounces is my units up there. On bottom, there are no units. I just have 1 times 1, which is 1. So that is 112 ounces over 1, or just 112 ounces. Or we might have, if we're looking at something we're not quite as familiar with, we might have 48 grams, and we want to know how many ounces that is. So we'll do the same thing. 48 grams, we'll put it in a fraction by putting it over 1. We have our relationship. 1 ounce is 16 grams. So over here, we have grams here on top. To get rid of them, we're going to put grams on bottom, converting to ounces. 1 ounce is 16 grams. So now the grams cancel out, cross-cancel. On top, we have 48 times 1 ounce, that's 48 ounces. On bottom, we have 1 times 16, that is 16. And we divide out. 48 ounces divided by 16 is 3 ounces. Now, I realize a lot of you can look at some of these measurements and just know, okay, I'm going from a small unit to a large unit. I have to divide. And if you can do that, that's fine. In the metric system, we can do the same type of conversion if we want to. We've got meters, grams, liters, decimeters, decigrams, deciliters, centimeters, centigrams, centiliters, millimeters, milligrams, milliliters. I'm going to stop there because the conversions will be the same if we kept going smaller. And we have decameter, decagram, and deciliter. Hecto and kilo. And we know that, this is 1, this is 1/10, 1/100th, and 1/1000th. This is 10, 100, and 1,000. If we have 7.2 grams, and I want to convert that into milligrams. Make my 7.2 grams over 1. Now in the book they use powers of 10. That's one of the reasons why we spent time with scientific notations, is working with powers of 10. But really, it's just as simple to look at this and say, okay, grams got to go on bottom. What's the relationship between grams and milligrams? Oh, 1 milligram is 1/1000th of a gram. Now, some might look at this and think this is a really ugly conversion, and it kind of is. The grams cancel out. 7.2 times a milligram is 7.2 milligrams. On bottom, 1 times 1,000th is 1,000th. I'm going to divide that out to be a decimal, 0.001. And now, just like up above, we have to divide it out. 7.2 milligrams divided by 0.001 is 7,200 milligrams. We might have 38 deciliters and want to know how many liters that is. So we can do the same thing. 38 deciliters becomes a fraction by going over 1. We're getting rid of deciliters and going to liters. So put deciliters on bottom so they're going to cancel out. And we know that 1 deciliter is 1/10 of a liter. So now again, the deciliters cancel out. On top, we have 38 times 1/10, which is 3.8 liters. On bottom, 1 times 1 is 1. So it's 3.8 liters over 1, or just 3.8 liters. Now, many of you are probably looking at this thinking there's a simpler way of doing this, and there is. I'm showing you this way just because we're going to get into some dual unit problems in a minute that some of you might find this easier to do. But if I wanted to go from 7.2 grams into milligrams, the way most of us were taught to do this is you look at the chart. I'm going from grams to milligrams. On my chart, grams to milligrams is 1, 2, 3 spots to the right. I can move my decimal point 1, 2, 3, filling in the zeros, spots to the right. That's 7,200 milligrams. If I have my 38 deciliters, converting into liters, same thing. On the chart, going from deciliters to liters, from deciliters to liters is 1 spot to the left on the chart. So I take my decimal point, it isn't shown, so it's at the end of the number, and I move it 1 spot to the left. I get 3.8. So our metric conversions can be done rather simply that way. Now that doesn't mean in the metric system we can completely ignore dimensional analysis. For the simple conversions we can. But the wrench in the system is there were a couple of units in the standard measuring system that were just so ingrained into medicine that they had to absorb them into the metric system. And the biggest one of that is the grain. A grain is abbreviated GR. Now be careful, don't confuse that with a gram. A gram is abbreviated just G. But because gram begins with GR, a lot of people see GR and they think gram instead of grain. So make sure you keep those straight. Remember we had said before that 1 pound was 7,000 grains. And that was used for measuring out that powdered medication. Because that was so, like I said, so set in the medical system, they absorbed that into the metric system for medical purposes. The problem was the conversion was not very clean. 1 gram turned out to be 15.4324 grains. And that's approximate. That's still rounded off a little bit. 1 grain turned out to be approximately 64.7898 milligrams. Now I'm going to show you here, if I use this to convert a gram to a milligram. How many milligrams are in a gram again? Everybody remember? One gram is 1,000 milligrams. There's 1,000 milligrams in a gram. So if I use this to convert these numbers, I make 1 gram, I'll put it over 1. I'm going to multiply, put a gram on bottom, and grains on top. 1 gram, 15.4324 grains. The grams have canceled out. Bless you. I'm going to put the grains on bottom now. 1 grain is 64.7898 milligrams. So now the grains have canceled out, and the only units I have left are the milligrams. So on top here, I've got 1 times 15.4324 times 64.7898. That is like 999.86 milligrams. And on bottom, I've got 1 times 1 times 1, which is 1. So we do get 1 gram is like 999.86 milligrams. So it's still rounded off a little bit. You can see it's still just a little bit off because we know that 1 gram should be exactly 1,000 milligrams, but it's not horrible. The problem is these numbers here, 1 gram is 15.4324 grains, is really ugly to remember. And 1 grain is 64.7898 milligrams, is also really ugly to remember. So they decided to just round them off in the metric system to create almost like a metric grain. And what they did is this. They said, we're going to just let 1 gram be 15 grains. That doesn't seem like such a stretch, right? 15.4 is going to just round to 15. The one that really seems awkward, I don't know why they didn't do, well, I'll make a note. This textbook uses 1 grain equals 60 milligrams. Now you'll note if I were to multiply 15 times 60, I get 900. That's trying to tell us there's only 900 milligrams in a gram. Doesn't work out. It's a severe round off. There are some textbooks out there that use 1 grain. 1 grain is 65 milligrams, which comes out much closer. 15 times 60 is 900, but it should be 1,000. 15 times 65 is 975, which comes out much closer. Like I said, there are some books that do say 1 grain is 65 milligrams, but a majority of the ones I've seen still say 1 grain is 60 milligrams. So that's something that to be aware of, that a grain could be defined differently, because it really is 64.79 whatever milligrams. So just something to be aware of if you're working with grains. Always make sure you clarify what those conversions are that are being used. In the field, I honestly can't say that I don't know which one they do use in practice the most. So if I needed to convert, let's say I have 3.2 grams and I need to convert that into grains. So 3.2 grams over 1. Put grams on bottom, grains on top. And we have 1 gram is 15 grains. The grams cancel out. 3.2 times 15 is what? 48. Grains over 1 are just 48 grains. Any questions? Okay. So that is your dimensional analysis for converting within each system. If I want to convert from standard to metric, or the other way or back, we have to know equivalencies. The problem is those equivalencies aren't real clean. They're all rounded off. For example, 1 kilogram is technically 2.208 pounds, but this textbook just uses 1 kilogram as 2.2 pounds. So they're keeping it rounded off. The one that kind of makes me chuckle in this book, 1 milliliter. Oops, I got to go there. I'm going the wrong direction. 1 fluid ounce. Come on, move right to it. There we go. 1 fluid ounce, I've always used as approximately 30 milliliters. And if you're looking in this textbook, on one page it does say 1 fluid ounce is 30 milliliters. About 2 pages later, it says 1 fluid ounce is 29.9 milliliters. It's somewhere in between there. It's like 29.94, to be honest. I'm going to use this one just because it's easier. But if you use the other one, obviously it wouldn't be wrong. Okay, so if we are told that we are prescribing .5 fluid ounces of medication, I want to know how many milliliters that is. Now, if we're loading a syringe, remember 1 milliliter is 1 cubic centimeter, so a milliliter is a cc. So I'm going to start out with my 1.5 fluid ounces, put it over 1 to make it a fraction. Fluid ounces will go on bottom so that they cancel out. Milliliters on top. 1 fluid ounce is 30 milliliters. So the fluid ounces will cancel out. 1.5 times 30 is 45 milliliters. And on bottom, 1 times 1 is 1. So that is just 45 milliliters. The most common conversion you will have to make between metric and standard is, of course, the 1 kilogram equals 2.2 pounds. And generally, it's going to be going from pounds into kilograms. You have a patient who comes in who states that they are 143 pounds. Well, we are going to put that over 1 so that we can convert them to kilograms. We're going to put pounds on bottom here so that they divide out. So kilograms will go on top. Now you'll see how I do this. I have the number I'm starting with, here, the 143 pounds. I put it over 1. In my conversion factor here, or my unity fraction, I put the units in first. I always put in this unit first because it has to be the same as this one because they have to cancel out. And then what goes up here is just what it's equivalent to or what I'm converting it to. And now that the units are in there, I go back and put in the numbers. Okay, 1 kilogram is 2.2 pounds. I put the 2.2 with my pounds. The pounds cancel out, cross cancel out. Now I'll multiply. 143 times 1 kilogram is 143 kilograms. On bottom, 1 times 2.2 is 2.2. And 143 divided by 2.2 is 65. So it's 65 kilograms. Any questions? So what if I have a substance that has a density of 12 pounds per gallon? And I want to know what that is in ounces per pint. $12 pounds per gallon, we have to recall, just like our rates from last week, That is 12 pounds over 1 gallon. And now we have to convert both units. It doesn't matter which one I convert first. I can either convert the pounds or the gallons. I'm going to start out with the pounds. Now, since pounds are on top, where do I have to put them over here? On bottom, so they'll cancel out. And I'm going from pounds into ounces. What's my relationship between pounds and ounces? 1 pound is 16. Good. So the pounds cross cancel. So now I'm going to have ounces. Now I have to get rid of the gallons. Now the gallons are on bottom here, so to cancel them out, I have to go on top here. I'm converting gallons into pints. Now I could just figure out what the conversion is from gallons to pints, but I'm not. We don't have a direct conversion from gallons to pints, but we do have a direct conversion from gallons to quarts. So I'm going to say 1 gallon is 4 quarts. The gallons cancel out. But now what I have is I have ounces on top and I have quarts on bottom. That would give me ounces per quart. I don't want ounces per quart. I want ounces per pint. So I have to keep going. I want to get rid of the quarts, so I'll put them on top. I need to get to pints, and I do have a direct conversion from quarts to pints. 1 quart is 2 pints. So now my quarts are gone, and I'm left with the pints. So now I do have ounces on top and pints on bottom. Those are my units, and that is what I want. So on top I have 12 times 16 is 192, times 1 is 192 ounces. On bottom, 1 times 1 is 1, times 4 times 2 is 8, and there's pints on bottom, so that's 8 pints. And then I divide out. 192 divided by 8 is what, 24? That is ounces per pint. Any questions?
Do another one?
Oh yeah, we're going to do a few of these. I'm going to cheat and look ahead. So now next, let's say we have a metric one in metric units. So we might have 340 grams per liter, and I want to know what that is in milligrams per milliliter. So 300, oops, hopefully I don't change my numbers. 340 grams per liter is 340 grams over 1 liter. And I want to convert that into, I need milligrams on top and liters on bottom. Now I could do this with my dimensional analysis like I just did. I could put grams on bottom, milligrams on top. I know that depends on how I want it. I say 1 gram is 1,000 milligrams. Or I could say 1 milligram is 1,000th of a gram, either way. That cancels out my grams. Now I have to get rid of liters, so I'm going to put liters on top, and I need to go to milliliters. I know that 1 liter is 1,000 milliliters. Or I can go the opposite way. I can say 1 milliliter is 1,000th of a liter. My liters are canceled out. 340 times 1,000 milligrams is 340,000 milligrams. 1 times 1,000 milliliters is 1,000 milliliters. If I divide this out, 340,000 divided by 1,000 is 340. That is grams per milliliter, or milligrams per milliliter. Yes, I realize it comes out to be the same number. Now, there's a simpler way they could have done this. I don't know if you could tell by the tone of my voice, this is the long way that this could have been done out. But if you get confused, you can always do it that way. But since these are metric, there's a shorter way we could do it. We could just convert each unit separately if we wanted to. We could do this with standard units too. It just gets really ugly decimals. But for metric, I want to convert 340 grams to milligrams. Now remember on my chart, here's grams, decigrams, centigrams, milligrams. To go from grams to milligrams, my decimal point is moving 1, 2, 3 spots to the right. So I move my decimal point 3 spots to the right, filling in those zeros. That's 340,000 milligrams. This should be milliliters here. I want to do 1 liter, then has to convert to milliliters. Same thing. This is liters, milliliters. To get from liters to milliliters on my chart is 3 spots to the right. So I take my decimal point and I move it 3 spots to the right. That'd be 1,000 milliliters. And then I just divide it out like I did up here. 340,000 milligrams divided by 1,000 milliliters is 340, and then it's just milligrams per milliliter. Let's do another example. Let's do 72 milligrams per liter. And I want to change that into milligrams per milliliter. So this is 72 milligrams per 1 liter. Now the top is staying milligrams. That's not going to change. The bottom is going from liters to milliliters. So 72 milligrams is going to stay 72 milligrams. 1 liter converted to milliliters, well, my decimal point from liters to milliliters is 3 spots to the right. So 1 liter is 1,000 milliliters. And I divide that out. 72 divided by 1,000 is 0.072. It is milligrams per milliliter. What do you think? Not horrible? Okay. I will say on this next test, it is the measurement conversions that people seem to lose the most points on, that they struggle with the most. Now, you are allowed to use your textbook and your notes on the test. I do also give you tables with the conversion factors on them to save you time if you need to. But make sure in the homework part for this week, you spend time on these, especially because students struggle with those, but also just on the regular measurement conversions, going from tablespoons to milliliters or whatever. People seem to really do struggle with those. Okay, the last thing we want to talk about is temperature. In all of the other conversions we've done, there's a common 0 point. For example, 0 inches is equal to 0 centimeters. Or 0 gallons is equal to 0 liters. There's a common 0 point. And having that common 0 point is what enables us to do the conversions with just the unity fraction. If we do not have a common 0 point, we cannot use a unity fraction. And temperature is a prime example of that. So our standard temperature is in the Fahrenheit scale. And in the Fahrenheit scale, we have 2 benchmarks. On the lower end, we use the temperature at which water freezes. This time of year, we're all too familiar with that. In Fahrenheit, what temperature is that? 32 degrees Fahrenheit. Good. And then we use the benchmark of the temperature where water boils. What temperature does water boil at in degrees Fahrenheit? 212. In the Celsius scale, which is the metric equivalent, can anybody tell me what temperature water freezes at? 0 degrees Celsius. And boils? Bless you. What temperature does water boil at in Celsius? 100 degrees Celsius. Good. This goes from 0 to 100. For that reason, sometimes it's called the centigrade scale. Centi meaning 100, grade meaning divisions. It's 100 divisions between freezing and thawing. So if you hear centigrade or Celsius, they do mean the same thing. But you can see here, not only is the size of a degree difference, because from 0 to 100 is 100 degrees Celsius to get from freezing to thawing. From 32 to 212 is 180 degrees on the Fahrenheit scale. So the size of a degree is different, but also the 0 point is different. There is not a common 0 point. So to convert from degrees Fahrenheit into degrees Celsius or the other direction, we cannot just use a unity fraction. We must use a formula. So if we have degrees Fahrenheit going into degrees Celsius, and we've used some of these formulas before when we were looking at evaluating expressions. Our degrees Celsius is equal to, we take our Fahrenheit temperature and we first have to subtract 32. What that's doing is bringing it down to a common 0 point. And then that is multiplied by, if I look at my 100 degrees here compared to my 180, that gives me a ratio of 5 to 9. So I multiply that by 5/9. So let's look at a common one, human body temperature. What do we commonly use in the Fahrenheit scale as our standard human body temperature? 98.6. There we go. 98.6. That's degrees Fahrenheit. What would that be in degrees Celsius? Well, we put that in here for F. So the first thing, we have to do our order of operations. We have to do the parentheses first. 98.6 minus 32 is 66.6. Then 5/9 times 66.6 is 37. So that's 37 degrees Celsius. So 98.6 degrees Fahrenheit is equivalent to 37 degrees Celsius. If I want to go from degrees Celsius into degrees Fahrenheit, I reverse this process. Remember when we talked about solving equations? You just look at how it was built and then you do the opposite. You take it apart. Well, here at Fahrenheit, they subtracted 32 and multiplied by 5.9 to go the other, or 5/9. To go the other direction, you would first take the Celsius temperature and divide by 5/9. Well, dividing by the fraction is the same as multiplying by its reciprocal. So it's the Celsius temperature times 9/5. Then we add back in the 32. So if you turn on the weather and they say it is going to be 20 degrees Celsius today, is that going to be a nice day or not? Well, let's take a look. So 9/5 times 20 plus 32. 9/5 times 20 is 36. Plus 32 is going to be 68 degrees Fahrenheit. So that's a decent day. Any questions? So I'm going to have you guys try one for me. About the coldest day I can remember in my life is we had raw temperatures. This is without the wind chill. It's about negative 40 degrees Fahrenheit. Do the conversion and tell me how many degrees Celsius that would be. This one you can actually just plug it into your calculator once you got the formula set up. You can do 5 divided by 9 and then times parentheses your negative 40 minus 32, close the parentheses. Did anybody get an answer before I hit equals? It's negative 40. Negative 40 degrees is the one temperature that's the same on both scales. Okay, so for next week, homework that we have, page 103, 1 through 19, the odds, is dealing with units of measurement. Page 110, 1 through 41, the odds, is dealing with converting between metric and standard units. Page 114, 1 through 25, the odds. This is that dimensional analysis that I mentioned, and do some of the basic ones. Look at some of the more difficult ones just so you're familiar with them. But if the more difficult ones are frustrating you, don't let it get you too wound up, because like I said, they take it to kind of an absurd level in the textbook. But make sure you are good at least canceling out the basic units within the fractions. Then we have page 118, 1 through 19, the odds. These are more of the units that apply to medicine, the apothecary units and household units. And finally, page 123, 1 through 21, the odds, is dealing with the temperature conversions. Next week, like I said, we will have our test, and that'll take at least the first hour. Usually it takes about an hour and 15 or an hour and 20 minutes. And we're going to try to put a 20 to 30-minute lecture in there before we're done next week. Like I said, before the halfway point of the class, we'll evaluate and see whether we're going to try to squeeze in a lecture or if we're just going to do the test and call her good. Okay, you guys have a great week. We'll see you next week.